Hello students. So today we have this question that says, consider the situation shown in the figure below. The system is released from rest and the block of mass 1 kg is found to have a speed of 0.3 meter per second after it has descended through a distance of 1 meter. Find the coefficient of kinetic friction between the block and the table. So before we proceed towards finding out the mu value, the coefficient of friction, we need to understand here that as the 4 kg and the 1 kg block are connected in some way, not directly but they are connected through some means, we can always relate their velocities and their displacements and their accelerations together using the constraint relations. So as we look at this figure, we should understand that the constraint or the equation that connects their motion is something like this, which says that if the 1 kg block goes down by, let's say, a distance x, then the 4 kg block must move a distance 2x in the same time. This we understand from the way the two bodies are connected. Yeah, for details you can go to the constraint relations and get to understand how we find out such a relation between the motion of two blocks which are connected like this. So if their displacements are related in this way, the same relation will hold true for their velocities also. So if 1 kg block is moving at any point in time with a speed v, the 4 kg block will have a speed of 2v, right? And the same relation is for acceleration also, though we don't require that relation here in this particular question. So when the question says that the block of mass 1 kg is found to have a speed of 0.3 meters per second after it has descended through a distance of 1 meter, understand that from the figure and the notations that we have given, it's been given that x is equal to 1 meter and v is equal to 0.3 meters. So once we know the displacement and the velocity of the 1 kg block, at that moment we know the displacement and velocity of the 4 kg block also. So this is the starting point. We need to know this much before we can start using our main equation for solving this question, which in this particular case will be the work energy theorem. As we see, there is friction acting on the 4 kg block because it is kept on a rough surface. We can't use the law of conservation of energy here because the energy is not conserved. So we shall be using the work energy theorem, for which we will first look for the forces that are acting on this system. So on the 1 kg block, we know there is this weight of the block acting downward, and the tension which is acting through the string, which we can relate with the tension in the upper string. So if we assume that in the upper string here the tension is T, it will be T here as well as here. So from there we understand that the tension in this lower string will be 2T. So the two forces acting on the 1 kg block will be mg and 2T. Both are along the same line, along the vertical direction in which the block is moving also. Whereas on the 4 kg block, the force that will take it towards right, as the 1 kg block moves down, 4 kg block will move towards right because of the force of tension acting on it. To oppose this motion in the rightward direction, frictional force, which will be kinetic in nature and having a value of mu n, which we all know, will be acting on the block towards left. Other than that, there will be normal reaction acting in the vertically upward direction, which will essentially balance the weight of this block, capital Mg we can call it. Yes, because the block is moving towards right in the horizontal direction. Along the vertical direction, there will be no net force on the block. So N will be equal to capital Mg. This is what we already know. So N is equal to capital Mg for the bigger block, for the 4 kg block. Now, if we try to use the work energy theorem here on the system, the work energy theorem, which says that work done by all forces on a system is equal to the change in kinetic energy of the system. As we try to use this theorem here in the situation, we see that there are two blocks in the system under study, and both of them are being in motion. So there are forces doing work on both the bodies. So we can write it as work done by, if we look at the work done by forces that are acting on the 1 kg block, work done by gravity which is acting on the 1 kg block, plus work done by tension acting on the same block. So we can write this work done on the 1 kg block plus the work done by tension on the 4 kg block, because 4 kg block is moving towards right, and as we see along the horizontal direction it is tension and friction in the opposite direction which are acting and doing work on the 4 kg block. Mind you, normal reaction and weight of 4 kg block are not doing any work because they are acting perpendicular to the direction of motion. So we can write the work done by tension plus work done by friction. These two forces are doing work on the 4 kg block. And this expression on the left side must be equal to the change in kinetic energy of the 1 kg block plus the change in kinetic energy of the 4 kg block. So when we try to now substitute all the values, we will get different terms for different expressions here. Let us do that. Work done by gravity on the 1 kg block, as the 1 kg block moves down through a distance of 1 meter. It will be the force of gravity, which in this case will be 1g, times the displacement, which is also 1 meter. So force into displacement, and since force and displacement are in the same direction, it will be with a positive sign, plus work done by tension on the 1 kg block. Understand that the tension acting on the 1 kg block is 2T. So 2T, and the displacement of 1 kg block is 1 meter but in the downward direction. So here the force is opposite to the displacement, so we will have a minus sign coming up here, work will be negative. So this is work done by tension on the 1 kg block. Now the third term on the left hand side is work done by tension on the 4 kg block. See that the tension acting on the 4 kg block is just T, and the displacement of the 4 kg block is 2 meters. For x being 1 meter, 2x will be 2 meters, and it is in the same direction as the tension, so it will be with a positive sign. T into 2 will be the work done by tension on the 4 kg block, plus work done by friction on the 4 kg block. Friction is acting in a direction opposite to the displacement of 4 kg block. So work done by friction will be the force of friction, Fk, whose value we will substitute a little later, times the displacement of the block. Since the displacement is opposite to the force of friction, it will come with a minus sign. So this gives us the terms on the left hand side of the work energy theorem, and this should be equal to the right hand side, which will be change in kinetic energy of 1 kg block, half the mass of the 1 kg block, which is 1, times the speed of the 1 kg block, square of that. So v squared, which in this case is given to be 0.3 squared. So this becomes the kinetic energy of the 1 kg block plus the kinetic energy of the 4 kg block after having travelled the distance. So it will be half m for the 4 kg block will be 4, times the velocity of 4 kg block, which will be twice of the velocity of the 1 kg block, 0.6 squared. So we have got the whole term on the right hand side. Let us simplify this equation. Now if you look at this equation, see that the work done by tension on the 1 kg block cancels out the work done by tension on the 4 kg block, and this also brings us to the result that work done by internal forces on a system is always 0. Here, since we have considered both the 4 and the 1 kg block as one single system, see that tension which is acting between the two blocks becomes an internal force, and then naturally the work done by tension in this case must come out to be 0, which is as it is coming out. So these two terms cancel out and we are left with 1g minus, now we can substitute the value of kinetic friction. It is mu n, and n we know it is capital Mg, which is 4g, the weight of the 4 kg block, times minus 2 the displacement, which is opposite. Okay, we have taken the minus sign here, is equal to, we can simplify the expression on the right hand side. So half we can take common, and inside will be left with 0.3 squared, which will be 0.09, plus 0.6 squared, which will be 0.36. So this is what we will be getting on the right hand side. Simplifying this further, maybe we can take g common from the left hand side, so that we are left with 1 minus 4 into 2, 8 times mu this multiplied by g on the left hand side is equal to, when we solve for the term on the right hand side, we will give half into this term in the bracket will be 1.53. Okay, there is a small calculation mistake here. There will be a 4 times 0.36 over here. So, we have to multiply that, and that is when you will get this number. And now you can simplify this further, take the g downward, so that you get 1 minus, this implies 1 minus 8 mu is equal to 1 by 2 into 1.53 divided by g, whose value will be 9.8. So, this can be simplified and it comes down to 0.078. And from here now, when we calculate for mu, it will come out to be 1 minus 0.078 divided by 8, which when you calculate comes out to be nearly equal to 0.12, which is the final answer.